It's time to learn more gas laws. Hi there, I'm Jeremy Krug, and welcome to my complete AP Chemistry course on YouTube. If you haven't already subscribed, go ahead and hit that subscribe button so that you don't miss a thing. Now, in our previous videos, we've been learning about the ideal gas law, some other gas laws that are very important in chemistry, and today we're going to be learning two more gas laws. The first one is called Graham's Law of Effusion. Now, Graham's law of effusion looks kind of intimidating when you see its equation, but as it turns out, it's not quite as difficult whenever you start doing the problems. Graham's law basically tells us that the rate of movement of gas particles is inversely proportional to their molecular mass. So, what does that mean? Well, here is what that equation looks like. And so we have a square root in there. And so to say this correctly, we could probably say that the rate of effusion of a gas particle is inversely proportional to the square root of that gas's molecular mass. And so we have rate of gas A over here, and the molecular mass of gas A is over on the right side in the denominator, and we have the same thing for rate B and molecular mass of B. Now this may look like an intimidating equation here, but actually it's not quite as difficult. But before we actually work a problem, let's define what effusion actually is. Now, effusion is not to be confused with diffusion. Most students know about diffusion because that's the movement of something from an area of high concentration to an area of low concentration. And that happens with gases as well. But effusion is specifically when molecules escape through a very tiny hole in a material. So for example, if you have a balloon, you blow up a balloon with your breath, or perhaps with some other device, and you may not be able to see it, but that balloon has little teeny tiny holes in it. And those tiny holes are, more or less the size of a molecule or the size of an atom, maybe a little bit more than that. And so these molecules of gas can escape through those tiny holes in the membrane of that balloon. And so whenever you have a balloon, you may notice that if it's a helium balloon, sometimes it will deflate or it will sink close to the ground. That's because the helium atoms or the helium molecules are escaping through the holes in the balloon. That's effusion. Now, Graham's law basically tells us that heavier molecules move more slowly than lighter molecules. And hopefully that makes more sense. If you think of a heavier molecule like xenon or radon or something like that, these are very massive molecules, massive atoms, and they move just more slowly. They're kind of lumbering along in space, or I should say through a membrane. On the other hand, very light atoms, light molecules like helium or neon or methane, these are going to be able to go really fast because they're light molecules. They don't have quite as much mass. So let's try an example here. Which gas effuses faster, nitrogen or helium, and how much faster? Well, the first thing that we have to do is determine the molecular masses of both of these gases. So we'll start with the nitrogen here. And nitrogen is N2. Hopefully we all remember that that's a diatomic gas. So here's nitrogen. It's got an atomic mass of about 14.007. So that means that N2, nitrogen gas, is going to be about 28.01 whenever we add that together. Now helium is a monatomic noble gas. Its molecular mass is very, very close to 4.00 whenever we round that off to 2 decimal places. So we can look at these two gases and say very definitively that helium is going to effuse faster. So we got half of the question answered already. But the key part of this is how much faster. This is where we're going to use the equation. I strongly recommend that you use the lighter gas to be gas A. Okay, always use the lighter gas as gas A. So that means that helium is going to be our gas A, and nitrogen will be gas B. And so whenever we put these numbers in here, well, helium, its mass is 4.00. That goes down here under the square root sign. And then nitrogen 28.01 will go up here on the numerator, so square root of 28.01. We can key this into our calculator and find that the square root of 28.01 divided by the square root of 4.00 is about 2.65. So you want to give your answer in a complete form. You want to say that helium effuses faster, and how much faster? 2.65 times as fast as nitrogen gas. So we can compare two gases and compare their rates of effusion based upon this gas law. Let's try another example that's a little bit more challenging. Helium can effuse 2.245 times as fast as a gas with what molecular mass? Well, this time the gas is a little bit different, isn't it? Or the question is a little bit different. We're being given a ratio, or being given one of the gases, and we're being told what's the other gas, or what's at least the mass, the molecular mass of the other gas. Well, whenever we plug in our substances here, which of the two gases is the lighter one? Is it helium or is it the mystery gas? Well, it's helium, isn't it? Because helium it says it's going 2.2 times as fast as something. So gas A should be helium whenever we write this down. And so B is going to be our mystery gas. We can call that X. Whenever we put some numbers in here, we use the molecular mass or the atomic mass of helium. So we'll put square root of 4.00 in the denominator over here, across. And we don't know what X is, so we're going to just call that square root of X. And we know the ratio this time. It's 2.245. So we're going to put that over here. So now we have an equation we can solve. I can cross multiply. So when I cross multiply in this direction, I get 2.245 times the square root of 4, which is 4.49. And when I cross multiply in this direction, that's just the square root of X. So now, to solve for X, I want to square both sides. So when I do that, I get that X equals about 20.2 atomic mass units. And so that's my answer. The molecular mass is about 20.2. Now, the question didn't ask me to identify the gas, but I suppose I could look up at the periodic table and see that there is a gas, a noble gas in fact, that has a molecular mass very close to that, which happens to be neon. So I could take a guess that this is very likely going to be neon. Now, it could be something else, but neon seems to be one of the most obvious choices here. So that's how we work problems with Graham's law of effusion. Now, I promised you 2 gas laws in this video, 2 for the price of 1, so we're going to do one more, and that's determining the partial pressure of a gas. Now, before we start talking about partial pressure, let's take a look at a very simple example to kind of get our feet wet here. Let's say we have this gas container, maybe a flask or something that's all sealed up, and we have a total of 10 gas molecules in here. 3 of them are blue triangle molecules, I'm trying to keep it simple, and 7 of them are red X's. So we have these 10 gas molecules. Now, if you had to guess here, what percentage of the pressure in that gas container is coming from the red X molecules? What percentage? Well, I hope you can see it's 7 out of 10, isn't it? So that would be 70% of the pressure. So if we knew what the total pressure in this container was, we could figure out the partial pressure, or the pressure that was coming from the red X's. Now we can do the same thing for the blue triangles. What percentage of the pressure is due to the blue triangle molecules? Well, it's 3 out of the total, 3 out of the 10. So that would be 30%, wouldn't it? So if we knew what the total pressure was in there, we could figure out 30% of that total pressure and see what the partial pressure of the blue triangle molecules were. Well, this is what helps us to understand what's called Dalton's Law of partial pressures. We've heard of John Dalton before. This is his law of partial pressures. Basically says that the partial pressure of a gas in a closed container is equal to the mole fraction, and that's what partial pressure is. The X is the mole fraction that gas is occupying in the mixture. You can express it as a fraction, you can express it as a percentage, times the total pressure in that closed container. So we're going to be solving for the partial pressure of gases in this gas law, and we're probably going to have to figure out the partial pressure of a gas, and hopefully we'll be given the total pressure in the container. So let's work a couple examples here, and then we'll see how this works. Let's say we have a flask that has a total pressure of 1.25 atmospheres. And let's say that this flask contains 7.2 moles of water vapor and 12.9 moles of carbon dioxide gas. So if that's the case, what is the partial pressure of water vapor? And then part B, carbon dioxide. So the first thing that we have to do here, or at least the first thing I would do, is draw a diagram. Just like we had in that last example. We had the X's and the triangles. This time, let's just draw a little diagram here. So here we have the total pressure, the 1.25 atmospheres. And inside the flask, we have 7.2 moles of water and 12.9 moles of carbon dioxide. So we're trying to find the partial pressure of the water vapor first. So the mole fraction of the gas, the X of the gas, is, if it's water, it's 7.2 moles divided by what? Well, it's divided by the total, right? So that would be whatever the sum of these two numbers is. I think it's about 20.1 total. So it's like in the last example, we had the 7 X's, and we divided that by the total number of shapes, of molecules, right? Well, it's the same thing here, divided by the total number of moles. Now, we have to multiply this by the total pressure, which is 1.25 atmospheres. So when we do this arithmetic, the pressure, or the partial pressure of the water, is 0.448 atmospheres. Now we can do the same thing for carbon dioxide. The partial pressure of carbon dioxide is 12.9 moles of carbon dioxide divided by the total moles of gas, which is still the sum of these, 20.1 total moles. And we have to multiply this by the total pressure, the 1.25 atmospheres. So when we do the math on that, it's 0.802 atmospheres. So here we have the answers. Those are the partial pressures of the two gases. Now, it's always a good idea, if you can, to go back and check your work. If we did everything correctly, the total pressure in this tank or in this flask should be equal to the total partial pressures of the individual gases. And if we add up 0.448 atmospheres with 0.802 atmospheres, I think we'll find that the total pressure is indeed 1.25 atmospheres. So that tells me that we probably did this right. So that's a good thing. Let's try an example that's a little bit more complex. Here we have a case where there's a gas chamber with a total pressure of 1.800 atmospheres. If 10 grams of oxygen gas and 10 grams of nitrous oxide, or N2O, are present in the chamber, what will be the partial pressure of oxygen and the partial pressure of nitrous oxide? So this question kind of sounds the same as the last one, doesn't it? Except this time, instead of having moles, we're given grams. And that's different because that means we have to convert from moles, or from grams, to moles. So we have our equation, but when we draw our diagram here, we're going to have to convert from grams to moles. So let's do that. We'll start with oxygen, since that's part A. So we're going to have to take the 10 grams of oxygen and convert that to moles. So in our conversion factor, we have to put grams on the bottom and moles on top. And this is O2, so that's about 32 grams per mole. And when we cancel grams and divide, we find that that gives us 0.3125 moles of oxygen. We can do the same thing for the nitrous oxide. We take 10 grams of N2O, and we're going to convert it to moles, so grams on the bottom, 1 mole on top. And when we add these atomic masses together, we find that it's about 44.01 for the molar mass on that. We can cancel grams and divide. It's about 0.2272 moles of oxygen. So now we're ready to actually solve the problem. So let's do oxygen first once again. The partial pressure of oxygen, to find the mole fraction, it's the 0.3125 moles that we got divided by the total moles. So how many total moles do we have here? Well, we have to add these two mole numbers together, and it looks to be about 0.5397 moles when you add them. And then, of course, we have to multiply the mole fraction by the total pressure. And the total pressure is 1.8 atmospheres. So we do that, and we find that the partial pressure of oxygen is 1.042 atmospheres when we key that into our calculator. We can do the same thing for nitrous oxide, and for that one, and there's a little typo here that should say N2O, not O2, but it's 0.2272 moles of N2O, correct that there, and divide that by the total moles, which would be 0.5397, and then we multiply by that by the total pressure, which is still 1.8 atmospheres, and when we do this arithmetic, we find that the partial pressure of the nitrous oxide is 0.758 atmospheres. So once again, it's very similar to the last problem, except in this one, we had to convert to moles first, which is not hard, but that's an extra step. Now let's check our work. Do the two partial pressures add up to the total pressure? 1.042 plus 0.758. Sure enough, that's very, very close, if not exactly the same as 1.80 atmospheres. So that means we did something right here. That's good. Now, let's try one more example. We're going to do an example that's very similar to something you might see on an AP exam or in a laboratory question, where we have a chemistry student who collects 0.1395 grams of gas over water in an experiment. The student runs the experiment at 25 degrees Celsius, and 50 milliliters of gas are collected. Today's atmospheric pressure is precisely 756 millimeters of mercury. The vapor pressure of water at 25 degrees Celsius is 24 millimeters of mercury. So do you understand what's happening in this laboratory question? We essentially have a pool of water here, so we can imagine like a beaker or some kind of pool of water here. We got the water, and we're actually collecting in a test tube over that pool of water. So we're somehow able to, collect some gas in here. The gas is bubbling out, and so we have some water in here, and so in this little area here, we actually have a mixture of water vapor and the gas. So there's a mixture there, and so we know that the amount of water vapor that's in there is equal to the vapor pressure of the water, whereas the gas is going to be whatever the rest of that is. So if we're going to calculate the partial pressure of the gas in atmospheres, we have to recognize that the total pressure in there is equal to the partial pressure of the gas plus the partial pressure, which is the vapor pressure of the water. So we're just going to have to plug these numbers in from the problem here. The total pressure is whatever the atmospheric pressure is. Outside here is going to have the same pressure as you have inside the test tube. There's no real difference there. So the pressure inside the test tube is 756 millimeters of mercury. So we can plug that in for P total. The partial pressure of the gas is what we're solving for. That's what the question asks us to solve for. And the partial pressure of the water vapor is the vapor pressure of water, which is 24 millimeters of mercury. So when you subtract, we can find that the partial pressure of the gas is just 732 millimeters of mercury. And that's the answer, right? Well, almost. We have to convert it to atmospheres. We got to do that little conversion. So we have to put millimeters of mercury on the bottom and atmospheres on top. And hopefully we remember that 1 atmosphere equals 760 millimeters of mercury. If you don't remember that, the AP test will give you that number in the equations section. So we cancel millimeters of mercury and divide, and it looks like it's about 0.963 atmospheres of the gas. Now part B is determine the number of moles of gas collected. Well, we have a pressure here, we have a volume of the gas, or the test tube here, we have a temperature. This sounds like a PV equals nRT problem. This is ideal gas law. We're just going to plug and chug. So the pressure is what we just calculated, 0.963 atmospheres. the volume of the gas, well, it says it was 50 milliliters of gas are collected. So we got to change that to liters, 0.05 liters. And then N, well, we're trying to solve for moles, so we're going to leave that as our unknown. We know what R is. R is the gas constant, 0.0821. And the temperature, well, this experiment was carried out at 25 degrees Celsius. So that's 298 kelvins. And then when we solve for N, we find it's 0.001968 moles. So we have the moles. Now, part C says calculate the molar mass of the gas in grams per mole. To do this, remember that grams per mole just means grams divided by moles. And the problem tells us how many grams of gas we have. It's up here. And we just figured out how many moles of gas. So we just divide. So grams would be the 0.1395 grams that we just got. And the moles of gas will be 0.001968 moles. And when you divide that on your calculator, you find that it is about 70.9 grams per mole. And of course, we're not asked to identify the gas, but we might look at the periodic table and say, well, that looks like it's about what chlorine gas would be, about Cl2, but we don't have to do that, but that might be a good guess. So this is a good example of a typical multi-part question you might see on an exam, on an AP exam, on maybe in your textbook or on your homework, something like that. I do hope that you enjoyed these videos. I hope you learned something about Graham's law of effusion and Dalton's law of partial pressures. If you learned something, then if you'd smash that like button, that would be wonderful. That way other chemistry students will be able to learn about my videos as well and learn chemistry too. I'm Jeremy Krug. I've been teaching AP Chemistry for a long time, and I want you to get an A in your chemistry class. If you're taking AP Chemistry, I want you to get a 5 on your AP exam. Thanks for watching, and I hope to see you again where we can learn some more chemistry together.